Hello students, welcome to this lecture on the static power, and in this particular lecture we will continue with the subthreshold leakage current and also subsequently see or look into the gate leakage current and then try to analyze the subthreshold leakage power and then the gate leakage power or the currents for a given circuit. Right, so let me pick up my pointer and proceed further to the next slide. So we were looking into the three series transistors, especially for the three input NAND gates, and we were looking into the logic of 1 0 0 in the previous lecture. Remember that for a three input NAND gate, the logic of 1 0 0 will yield an output logic of 1 here. So that means that the pull up side, so the pull up circuit is likely to make sure that the output voltage is retained at VDD, because the pull-up side we will have the two of the transistors where the input is 0 0 is going to make the transistors, PMOS transistors, both the PMOS transistors to be on, and the PMOS transistors are going to drive the current to ensure that the output voltage is charged to VDD value, right? Now we are interested in finding out the static power or the subthreshold leakage power in this particular case. So we know that when the transistors are getting an input of 0 0, especially for the NMOS transistor, we know that these two transistors will be off, and the transistor with the logic of 1, this will be on. And if I consider this particular transistor, the on transistor, to be working as a pass transistor, on one side of the diffusions, or one side, or rather the drain terminal here is connected to the, or is being charged to VDD rail, then the other side it can charge, or it can drive till VDD minus VT. So if I have this particular node voltage as VDD minus VT, and these two are off transistors, on the other side it is connected to the ground, then I should be able to estimate or evaluate the subthreshold leakage current. Right, and then that is what we had done, VDD minus VT, and then ground the subthreshold leakage current of 1. Using that particular, the approximate equation of the subthreshold leakage current, we estimated, we arrived at an expression of subthreshold leakage current for the transistor number 1, and then the subthreshold leakage current for the transistor number 2. Equate both the subthreshold leakage currents, we should be able to find out Vx value, which was 0.05529 volts, and then find out the subthreshold leakage current. Turned out to be 0.1135 multiplied by I of current, which is actually, and if I compare that with 1199 I of, which is for the two stacked transistors, with on one side it is VDD and the other side it is ground. So this particular value is higher than this particular 0.1135. And intuitively we can you can say that that is correct, because this VDD minus VT, which is a slight drop in the voltage as compared to the VDD value. Right. So if I have it three transistors, stacked transistors, with one of them being on, the two of them will give me the off transistors. The two of the NMOS transistors which are off are likely to give the subthreshold leakage current, but this current will be 0.1135 of the I of current. Right. Hope this is clear. Now let's say that if I have a logic of 0 1 0. Right, if I have a logic of 0 1 and 0, so this is off transistor. Of course, the 0 1 0 will give me the output of the 3 input NAND gate to be nothing but 1. That means that the pull up side it is active and it is driving the output node to value of VDD. So in this 0 1 0, both these transistors are off, and then this particular transistor where the 1 is given, or logic level high is provided to the gate of the second transistor, that particular transistor will be on. And if I have that on transistors, and normally when we see the two stacked transistors or the three stacked transistors where the first transistor is off, so if I consider this particular transistor where both the transistors are off, one has noticed that this particular node voltage, right, if this is an off transistor, I will have the subthreshold leakage current. This subthreshold leakage current is so low that it is in terms of the nanoamperes for a 65 nanometer technology node. This particular node voltages turns out to be very, very low. It is actually somewhere around 0.00 some value. Right, 65 value or 5 volts or something like that. So 0.05 or 0.06 volts. right? So in that sense, this particular, if I have an off transistor here, this Vx value is going to be really low value. And if I have a low value here, the Vx value, and this is an on transistor, so it can work like a pass transistor, and it can pass whatever is there on the other side. Even though I have written Vx and Vy as two different variables, it turns out that because it's an off transistor here, Vx value will be very low, right? So a low value here is going to have a reflect on the Vy value, right? So we will have this Vx is equal to Vy, right? So if I consider these two node voltages as the same, then I can actually have these two transistors, the three stacked transistors, in which one, the middle transistor is on. I can actually make it an equivalent of two transistors, taking out the on transistors, and then having this node voltage of Vx equated to Vy, right? And these two transistors will be stacked. These two off transistors will be stacked. And now I think I should be able to find out the subthreshold leakage current quite easily. I have the subthreshold leakage current of 1, I have the subthreshold leakage of 2, and then on one side it is VDD, the other side it is ground, so it will be nothing but 0.1199 of the I off current. And this is something which we have already seen earlier, right? So for a logic of 0, 1, 0, I will have a subthreshold leakage current of 0.1199 of the I off current. Moving ahead. So now let's take a look at the gate leakage component. So the gate leakage component is there especially for an on transistor. Now remember that the subthreshold leakage current we actually evaluate for a transistor where the VGS value is less than or equal to 0.3 volts or the VT value, right? So generally we take into account the VGS value is actually less than 0.3 volts for the subthreshold leakage current, and then subsequently the subthreshold leakage power estimation. For the gate leakage current and then estimating the gate leakage power, we need to ensure that the transistor, only the on transistor is likely to give us the gate leakage current, right? And the gate leakage current is actually attributed to the tunneling effect, the tunneling current through the oxide dielectric layer. So let me draw a cross-section diagram of the NMOS transistor quickly. So this is my N plus diffusion pocket, N plus diffusion pocket. And this is the oxide, and then this is the gate, right? So what is likely to happen is, based on the voltage applied here, if it is a 1 volts logic for a 65 nanometer technology node, and let's say the source is grounded, I will actually get a current that will be flowing or tunneling from the gate to the source side, right? From the gate to the source side. So I will have a current, and this particular current is called as the gate current. All right. So when I consider this particular circuit of two stacked transistor with Y is equal to VDD, this could be a part of a 2-input NAND gate where we have 0 and 1 as an input. So my output will be nothing but 1 for a 2-input NAND gate, right? It will be active or driven by the pull-up side. So the pull-up side is going to make sure that the output node voltage is set or configured at VDD. So in this case, I have a 0 and a 1, so I will have some kind of a subthreshold leakage current. But more importantly, when I'm looking into the gate leakage current, this one is likely to give me a gate leakage current or a tunneling current across this oxide, right? And that is referred to as I current gate for the first transistor. So this is the first transistor. For the second transistor, this is an on transistor. So whatever is 0 here, it is kind of passed into the other side of 0 volts. So this VGS turns out to be 0. So that means that this is not likely to provide any gate leakage current. So that's what I have written or indicated here. VGS of the first transistor is actually 1 volt or VDD value. So it is likely to give me a gate leakage current. So that is represented by IG of one transistor. VGS of the second transistor is going to be 0. In fact, if it is actually less value, maybe it is 0 or a VT value, right? This is going to give me a very low gate leakage current, right? So if it is close to VDD value, I will get a gate leakage current. So what it really means is just to summarize the gate leakage current, which will help in evaluating the gate leakage current and then subsequently the gate leakage power, is we need to identify in a circuit which of the transistors are on, and then from then we should be able to find out the gate leakage current. Right. So if I have another configuration here of the transistor here, which is on, and the transistor on the down transistor, which is closer to the ground rail, it is off, and this is provided with a 0 logic, and this is 1. So this 0 is going to, this is anyways an off transistor, so there won't be any gate leakage current. But having a 1 logic here, although the transistor is on, what happens is, because on the other side it is VDD, so it is going to act like a pass transistor. And in this particular node, we will have VDD minus VT. So my, the VGS for the transistor number 2, right, is going to be VDD minus of VDD minus VT, which is actually turning out to be VT value. If VT value is actually closer to the 0 volt, so the gate leakage current will be actually be very, very small, and we tend to ignore that. So what we are saying is the negligible gate leakage current is evaluated if the off transistor is closer to the rail. So in this case, I had a VGS value of VDD, so I got the gate leakage current. But if we swap the logics here, 0, 1 onto the 0 to the transistor, which is closer to the rail, and 1 to the transistor, which is closer to the output node, then I will have the VGS value to be very, very small, and that will have a very reduced value of the gate leakage current. So this particular configuration is better in terms of the gate leakage current, just to minimize the gate leakage currents and overall minimize the gate leakage power. Right? Hope this is clear. Moving ahead. So we had seen the subthreshold leakage current for the NMOS transistor. We had seen the gate leakage current for the NMOS transistor. The subthreshold leakage current for the PMOS transistor is also very, very similar, just that we'll have to write those voltage terms in terms of VSG for the PMOS transistor, and we have to write the source to body will be nothing but body to source, and we have to write VSD instead of VDS, and our expression will remain the same. For the PMOS, the gate leakage current of the PMOS, it turns out to be very, very less, turns out to be 1/10 that of the NMOS transistors, with the similar VGS effect. If the VGS for the NMOS transistor is 1, and if I have the VSD for the PMOS transistor to be 1, I will still get the gate leakage current to be 1/10 that of the NMOS gate leakage current. The reason is actually very simple, because for the NMOS, while we get the tunneling current, the majority carriers in the NMOS, which is nothing but the electrons, which actually tunnel from the body or the source side to that of the gate side. So that kind of tunneling, or the flow of the majority carriers on the NMOS side is much easier as compared to that of the PMOS, where the holes are the majority carriers that is lying in the channel or that is lying close to the source side, and that has to tunnel to the gate side, and that sees a lot more barrier. So in that sense, the PMOS, the tunneling current turns out to be very, very low for the same amount of the VGS value, for the same magnitude of the voltage values. So in that sense, what we are going to do is, just for our own analysis, this current is turning out to be very, very low. So we will direct it to a value of 0. So from here on, while we are looking at the circuit, it may be a NOR gate or a NAND gate or any other combinatorial circuits. The PMOS gate current, we will approximate it to be 0. And we will try to evaluate the subthreshold leakage current for the PMOS. We will also evaluate the subthreshold leakage current of an NMOS and then the gate leakage current of an NMOS. And finally, we will sum up all the leakage currents and including the gate leakage current and the subthreshold leakage currents, and then try to evaluate or analyze what is the leakage power, also referred as the static power. Right? So hope this is clear. So let's take a look at the 3-input NAND gate, which we have anyways taken a look at it, but with some values now. So if suppose I have a logic of 0, 0, 1, that means that the output is actually nothing but 1. So that means the output is driven by the VDD, by the pull-up side of the 3-input NAND gate, which is nothing but consists of 3 of the PMOS transistors in parallel. The values given here is, the gate leakage current for an NMOS is 6.3 nanoamperes. The gate leakage current of the PMOS is 0, and these are the typical values for a 65 nanometer technology node. The I off current of the PMOS transistor, that means when the PMOS transistor is off, I will get a current of 9.3 nanoamperes, and if the NMOS transistor is off, I will get a current of 5.63 nanoamperes. Right, so remember that the I off current, the subthreshold leakage current of an NMOS is actually less than that of the I off of the PMOS transistors. All right, so what it really means is, if I apply the same magnitude of the voltages, the PMOS is likely to give me slightly more subthreshold leakage current than that of the NMOS transistors. Right. So looking at this particular, the pull down side, because the pull up is going to be active. The pull down side is where we will get the leakage current. And if it is the logic of 0, 0, 1, that means 0, 0 and then 1. So the 1, the transistor which has a 1 which is on, it is actually closer to the ground rail. So this acts like a pass transistor and then provides this on the other terminal. It is going to pass a 0 voltage. So my subthreshold leakage current, because of these two stacked transistors, on one side it is VDD, on the other side it is 0 volt. So it will have 0.1199 of the I off current. The I off current of the NMOS side is 5.63, so it will be nothing but 0.675 nanoamperes, right? And if so, this we calculated for the subthreshold leakage current. So we need to evaluate for the gate leakage current. So the gate leakage current, if I consider, we need to identify the on transistor, and only this transistor is on, where we get this VGS value to be nothing but 1 volts. So it is not close to VT or close to 0. So I will have some gate leakage current, which is nothing but the 6.3 nanoamperes, which is given in this particular data sheet, right? So this becomes the subthreshold and then the leakage current for the 001 logic. Now, if I look into the pull-up side of this particular 3-input NAND gate, I will have 3 of the parallel PMOS transistors. So let me draw that as well, so that and see whether there are any kind of a leakage currents. So on one side it is VDD, and on the other side also it is actually VDD, because this is a PMOS or the pull-up side. And the logic here that has been imparted or given to the transistor is 001. So that means this particular transistor is off on the pull-up side, that is on the PMOS side, whereas these two transistors are on, right? And it ensures that this is the output is charged to VDD. So there won't be any leakage currents here, because this is anyways an on transistor. There should be a subthreshold leakage current here, but if you look into the VDS value, right, the VDS value turns out to be the same. And whenever we have the same drain to source potentials to be the same, there won't be any current. In fact, there won't be any subthreshold current as well, because on both the sides of these transistors, we have the current of VDD. There should be some kind of a potential difference, then only we will have some kind of a subthreshold leakage current. But here, because both the terminals of this transistor, which is an off transistor, sees the same potential, so we will not have any subthreshold leakage current. This particular on transistor was supposed to give us the gate leakage current, but because we know that the PMOS transistor is likely to give a very reduced gate leakage current. So although it is a 0, what we are going to say is that the current here and then the current here that is tunneling to the gate side is going to be very, very low. And in fact, the gate leakage current of the PMOS side is going to be 0 and then 0. The subthreshold leakage current on the PMOS side is going to be 0. So the total leakage current, for this particular logic of 001 turns out to be 6.3 nanoamperes plus 0.675 nanoamperes. And if I actually do a multiplication by 1, which is nothing but the VDD value, I should be able to find out the static power for this particular logic. Right, because the one VDD value is there between the rail voltages of VDD and then that of the ground. Right, so it is likely to have a current consumption of 6.3 plus 0.6795, which turns out to be 6.975 nanoamperes. And if I have to multiply by the, if I want to estimate the power, it has to be multiplied by the rail voltage, which is configured to the VDD value of 1 volts. Right, hope this is clear. Moving ahead. So let's say the logic is 0, 1, 0. So for a logic of 0, 1, 0, and this is something we had already seen in the previous lecture. For a logic of 0, 1, 0 here, we know that, if I want to understand or estimate the subthreshold leakage current, this value is going to be very, very low. This value is going to be very, very low. And so I can say that Vx and Vy were going to be same. On one side it sees VDD and the other side it is ground. So I can actually have two stacked transistors, on one side with VDD, the other side as Vy, because B transistor which is on is going to act like a pass transistor and make this Vx is equal to Vy. So the subthreshold for the two stacked transistor will be 0.1199 of the I of current. Turns out to be 0.675 nanoamperes. Now, if I want to find out the gate leakage current, the gate leakage current is applicable only for an on transistor. So only the B transistor is on here. So I will have this transistor as an on transistor. So I should have a gate leakage current. The value of Vx here and then the Vy here. All right, I should be able to find out from the subthreshold leakage current. Turns out to be very, very low value, 0.06 or 0.7 values. So in this case, I will have the VGS value to be almost close to the 1 value. So I will get the gate leakage current not equal to 0. Right. So if you remember, when we started with the gate leakage current, if it was connected to VDD, right, or rather it was connected to an output node which was at VDD, and then two of the stacked transistors where I had one this one and then 0 this one. So this one on transistor is going to act like a pass transistor and then going to supply VDD minus VT, and then we said that okay, this the gate leakage current here will be very, very low because the voltage here VGS value turned out to be closer to 0 because it is nothing but 1 minus VDD minus VT, which will be nothing but VT. So my gate leakage current turned out to be 0, right? But in this particular case, because of this transistor off transistor, I will have a Vx value which is not VDD minus VT. In fact, this Vy value is not VDD minus VT. It will be very, very close to 0 volts, and that is the reason why I will have a gate current and it will not be equal to 0. In fact, the gate current will be close to the gate NMOS side will be close to 6.3 nanoamperes. On the pull-up side, we will have a similar effect as that of the logic and as that of the previous logic. We will not have the subthreshold leakage current on the pull-up side, and the gate leakage current, although there are two transistors which are on, but still we will ignore it, saying that the gate leakage of the PMOS is very, very reduced, value very, very value close to the 0. And hence we will not take that into account. Right, hope this is clear. Moving ahead, if my logic is 0, 0, 0, we know that the output in this particular case will be 1. That means all the three transistors are on. All right, there won't be any subthreshold leakage current from the pull-up side. There will be the 3 gate leakage current, but we know that the gate leakages of the PMOS transistors are very, very negligible, and then so that we are going to ignore that. For the 0, 0, 0, all the 3 transistors are off, so the subthreshold leakage current will be nothing but 0.101 of the I of current, as we had seen in the previous lecture. Gate leakage current, because all the transistors are off, so we will not have any gate leakage current. So the subthreshold 3 stack current will be the total leakage current coming for this particular logic. So it turns out to be 0.568 nanoamperes. Moving ahead, if the logic is 0, 1, 1, so I have 1 and 1 here, and then 0 here. So I can consider these two on transistors to work like a pass transistor. So the potential of 0 can be passed here, the potential of 0 can be passed here. I will have a gate leakage current coming from this on transistor, a gate leakage current coming from this on transistor. So the total gate leakage current is actually nothing but twice that of the gate leakage current for an NMOS transistor. So so the gate leakage current will be for the transistor B and C. So 6.3 plus 6.3, 12.6 nanoamperes will be the total gate leakage current for this particular 3-input NAND gate for a logic of 0, 1, 1. Well, for if I want to find out the subthreshold leakage current, we know that only one transistor is off here, the other two are on. So we will have the 0 volt here on one side, the other side it is VDD. So I will have an I of current for this particular A transistor, which is nothing but 5.63 nanoamperes. So the total leakage current will be 5.63 plus 12.6 nanoamperes multiplied by 1 volts will give us the static power. right? Moving ahead, so 3 input NAND gate, let's see for the logic of 1 0 0 and logic of 1 0 1. For a 1 0 0, if I have 1 and 0 0, this 2 will be off transistor, this will be an on transistor. So I will have this transistor working like a pass transistor, so I will get the voltage of VDD minus VT here. This 2 off transistor is likely to give me the subthreshold leakage current. This on transistor will have a gate leakage current, but because this VGS value turns out to be close to VT, so I will have the gate leakage current negligible or very low value, and then I can equate it to 0. The subthreshold leakage current, we know that for a VDD minus VT and then the ground, if there are 2 stacked transistors, it turns out to be 0.1135 of the I off current. Turns out to be I off current is nothing but for an NMOS is 5.63, so it will be 0.639 nanoamperes. For logic of 101 here, these 2 transistors will be on. On one side it is working like a pass transistor, so the ground of 0 will be passed, or a 0 logic will be passed here. On this particular transistor, which is also an on transistor, so it says y is equal to VDD, so it will pass VDD minus VT, the NMOS transistor. So this off transistor is going to give me the subthreshold leakage current. And then so the subthreshold leakage current will be nothing but the I off and 10 raised to VGS. In this particular case it is 0 plus eta. VDS, it is nothing but VDS minus VD, so I'll have minus VT, and then minus of K gamma, and then VSB is nothing but 0 divided by the slope of S. So S is 0.1 and eta is 0.1, so I can cancel that. So it is nothing but I off into 10 raised to minus of 0.3. So this turns out to be nothing but 0.5 value. Right, so 0.5 of the 5.63 nanoamperes. The gate leakage current, because this is VDD minus VT, I will have a negligible gate leakage current here from this particular transistor. Right, the gate leakage current is 0. This is anyways an off transistor, so I will have no gate leakage current. I will have a gate leakage current coming from here because the VGS value here is actually 1 volt. So I will have a gate leakage current of the one single NMOS transistor, which is 6.3 nanoamperes. Right, so moving ahead, so this is what we had seen actually for the logic of 101. So the I subthreshold for the leakage current is what is stated here, 10 raised to minus of 0.3, so 0.5011 of I off, and I off is 5.63, so it will be 2.815 nanoamperes.